In previous theorem, we have shown that the limit of sequence of measurable functions is again a measurable function. In this, now in the next theorem, we will see that if we have a given bounded sequence of measurable functions, then the limit, limit superior and the limit inferior are both measurable functions. So given a bounded sequence of measurable function, we will show that the limit superior and the limit inferior of that sequence is also a measurable function. So let us state this theorem here. Let fn of x be let fn of x be a bounded sequence, bounded sequence of measurable functions, bounded sequence of measurable functions for each x in x. Then the limit superior of f and x and limit inferior of f and x and limit inferior of f and x is are bounded functions, are bounded are measurable functions, are measurable functions, are measurable functions, are measurable functions, are measurable are measurable functions. Proof. So first I will try to explain what do we mean by limit superior. Suppose we have given suppose we have a given sequence of real numbers. Say let a and b a sequence of real numbers. Let a and b a sequence of a and b a sequence of real numbers. Then limit superior is defined by limit superior of this sequence a n is equal to the it is infimum n greater or equal to 1, supremum k greater or equal to n ak. Okay. So that's the definition of limit superior, and this can be written as the infimum can be written as this: the meet n greater or equal to 1 means n runs from 1 to infinity, and supremum means the join k greater or equal to n means k runs from n to infinity of sequence. So that's limit superior of the sequence a n. So you can see this example. Let's see this example. See this example. If an is equal to minus 1 power n, then you can see then the limit superior of an is equal to 1. You can easily verify this. Limit superior of an is 1 because it is first you are taking the supremum an. Supremum means an where k runs from 1 to n, that means it is the supremum of minus 1 power n, which is equal to 1. And then you take the infimum of those one as it's equal to 1, because that's now now let's if we apply first supremum, then it will be the bounded sequence. Okay, it will be the constant sequence, and each term of the sequence will be 1, because for k runs from n to infinity it will be 1 supreme minus 1 power k runs from n to infinity, this will be equal to 1. And then you take its infimum, that's again equal to 1. It's very simple. Now here we have here the bounded sequences. Here this is the sequence in our theorem. Here f and x is a bounded sequence, is a bounded sequence of measurable functions for each x belongs to x. Okay. We show that limit period of f and x is a measurable function, is a measurable function. So what's limit period? As already explained, we have this limit period of f and of x is equal to meet and runs from 1 to infinity, then join k runs from n to infinity fk x. That's the limit period. Let's fix this next for each fixed natural number, and we define a function hm. Fix a natural number n. Fix a natural number n and define, let's define this hm, which is equal to say it's equal to fn plus 1 join fn plus 2, so on up to fn plus m. It's equal to fn plus 1, it should be, it's fn plus 1, fn plus 2, hm is equal to it's first fn, it starts with fn. Okay, there is this one here. Okay, so it's fn join fn plus 1 join, so on up to join fn plus m. And then you can see this hm, then hm, hm, it's it's increasing sequence. Then hm, then this hm is an increasing sequence of measurable functions. Increasing sequence of measurable functions. Why it's an increasing sequence? Because if you take h1, what's h1? H1 is fn join fn plus 1. Then you take h2. H1 will be the join of fn plus 1, fn plus 2. So actually, H2 is the supremum of bigger set than the H1, because H1 is the supremum of Fn and Fn plus 1. H2 is the supremum of Fn, Fn plus 1, Fn plus 2, and H3 will be the supremum of Fn, Fn plus 1, Fn plus 2, Fn plus 3. So you can see this Hm, it's actually increasing sequence. Also, it's measurable because we know that join of two measurable functions is again a measurable function. It's done in the, you can see lecture 8 or 9, where I have seen that if we have two measurable functions f and g, then their join. If we have two measurable functions f and g, f and g are measurable functions, f and g are measurable functions, then their join, f join g, it's again a measurable function. Join of two measurable functions is again that means join of finite measurable functions is again a measurable function. You can see if it is true for two measurable functions, it will be true for any finite, say f g h or f1 f2 so on f3 fn. So here we have here m plus 1 measurable function is fn plus 1 so on up to fn plus m. They are m plus 1 measurable function. Their join is again a measurable function. So hm is measurable function and it is also increasing sequence. So I can write this hm is an increasing sequence of measurable functions. Is an increasing sequence of measurable functions as each hm is measurable, and one can easily verify that this hm it's less or equal to hm plus 1 for all m greater or equal to 1. And since also this hm is bounded, therefore also hm is bounded and it is increasing sequence. Also this hm of x is a bound because fn of x is a bound. Hm of x is a bounded sequence, is a bounded sequence. Therefore so therefore it's a bounded sequence. Therefore limit m approach to infinity, hm it exists. And since this hm is increasing sequence, its limit exists. That means the limit of hm must be equal to its supremum value. Limit of hm is equal to the supremum of hm, and that's equal to the supremum of this m greater or equal to 1. Okay, m greater or equal to 1. So it's equal to supremum of fn join fn plus 1 join so on join fn plus m, where m is any value greater or equal to 1. Greater or equal to 1. Okay. It is supremum of fn join fn plus 1 join so on plus fn plus m, where m is greater or equal to 1. So that's equal to the supremum of actually fk, where k is greater or equal to 1. You can see this. K is greater or equal to n. Sorry, k is greater or equal to n. So it's fn plus 1 so on. So this is equal to the join k runs from n to infinity fk. So this is your limit of hm, where hm is a measurable sequence of measurable functions. But we know that in previous term we have seen that the limit of sequence of measurable functions is again a measurable function. Therefore, this limit is a measurable function by previous theorem, this joint k runs from n to infinity. Fk, let me denote this by gn because it will be the function of n. Gn is a measurable function, is a measurable function, is a measurable function. This is true for each n greater or equal to 1. So in other words, it means that this implies that Gn is a sequence of measurable functions. It's a sequence of measurable. It's a sequence of measurable functions. And one more thing, this Gn is decreasing sequence because G1 will be the supremum k runs from 1 to infinity. G2 will be the supremum k runs from 2 to infinity. So G2 is the supremum of the smaller set than the supremum of G1 because G1 is the supremum of F1, F2, so on up to infinity, and G2 will be the supremum of F2, F3, and G3 will be the supremum of F3, F4, and you can see this G4 will be the supremum of F4, F5, so on and so forth. So you can see this Gn is decreasing sequence. G1 will be greater or equal to G2. Also this also you can see this Gn is a decreasing sequence, is a decreasing sequence. Okay. So that means Gn is a decreasing sequence of measurable function, and also Gn is bounded, therefore its limit exists. So this implies a limit of Gn exists as Gn is a bounded sequence, is a bounded Gn of x. Gn of x is a bounded sequence for all x in x. For all x in x. And Gn is decreasing sequence. This implies limit of Gn will be equal to infimum of Gn, n is greater or equal to 1 because its decreasing sequence, the limit of a decreasing sequence is equal to its infimum value. But that's the notation for the infimum is this, and runs from 1 to infinity of Gn, and that's equal to, this is equal to, and runs from 1 to infinity. What's Gn? Gn is a join. Gn is this limit is the infimum is the meet. It's the meet actually. It's not join here. It's meet. Okay. Okay. This is the meet and runs from 1 to infinity of Gn. That's equal to meet and runs from 1 to infinity. Then join. Gn is join. K runs from n to infinity of Fk. So that limit is actually the limit period of Fn. Okay, but we know that limit of sequence of measurable function is again a measurable function. Therefore, this limit is a measurable function. This is a measurable function, and this limit is equal to the limit period of Fn. So we can see this limit period of Fn is equal to the limit of Gn, which is measurable, which is measurable. So thus limit period of fn is a measurable function. Thus limit period of fn is a measurable function. Also this limit inferior, what's the limits inferior? Also limit inferior of fn, it's equal to the minus times limit period of minus fn. But limit period of fn is measurable, therefore limit period of minus fn is also measurable, and minus times the limit minus times the measurable function is again a measurable function. That means minus limit period of minus fn is a measurable function. So which implies that limit inferior is a measurable function. So this implies limit inferior of fn is a measurable function. So that proves the theorem completely. Now next theorem we will prove Agraw's theorem. It's the Agraw theorem. Agraw theorem. First, let's write its statement. Let fn be a sequence of measurable functions. Let fn be a sequence of measurable functions such that fn converges to f almost everywhere, and let E be a measurable subset, of X such that measure of E is finite, such that mu star of E is finite, it's less than infinity. Then for all epsilon positive, there exists a measurable subset f of E. There exists a measurable subset f of E such that measure of E minus f, such that measure of f is less than epsilon, such that measure of f is it's less than epsilon, and this sequence is fn, and the sequence fn converges, and the sequence fn it converges uniformly to f, converges uniformly to f, converges uniformly to the function f on this set, on E minus f, on E minus f. So this fn it converges almost everywhere. It's a sequence of measurable functions such that this fn this sequence fn it converges to f almost everywhere, and E is a subset of measurable subset of X such that its measure is finite. Then for each epsilon positive, I can find a subset f of E such that outside of that set f, So we can F and it converges uniformly to F on E, outside of F, okay, on E minus F. This is a very important theorem because it's only given that this Fn converges to F almost everywhere. Okay, and from this convergence we find the uniform convergence on a set E minus F where measure of F is very small. If we remove that portion from this E, then the convergence will turn out to be a uniform convergence. Proof. First, can remove null sets here without loss of generality. That's an exercise for you. Without loss of generality, we can assume that Fn of x converges to Fx for all x, not almost everywhere, for all x and x. So this you need to verify. Okay. It's very simple. We remove the null set from the set X, and then we work. Then we'll do work on the measure space on the rest of the set. Okay. On that set, Fn converges to F for each x on that set. And E subtract x, therefore E will be subtract that set. Okay. Actually, here we are given that this Fn of x, Fn converges to F almost everywhere. So that means there is a set A such that Fn of x converges to Fx for all x in A, and measure of A complement is 0. Then we take this space. Y is equal to x minus A. Then we take the space y is equal to x minus A. When we take this space, y is